Hi everyone, my name is Zafeirios Fountas. I'm one of the organizers of the workshop today, and I'd like to thank you all very much for being with us today in the first workshop on temporal representation in reinforcement learning. So let's go to see what this workshop is all about. I think that in any way that you look at it, time is a fundamental dimension of existence and experience. Understanding time essentially means understanding change, and it's not even easy to imagine an organism without the ability of processing temporal information at some level. We can see that in nature, for example, where most creatures do rely on temporal estimations for their survival. This includes forager honeybees, for example, that need to estimate how long it takes for a colony to find food storer bees in order to adjust the rate of collecting nectar, while even most plants need to keep track of time of the day using multiple cues, for example, the position of the sun, in order to know when to perform time-sensitive operations, such as flowering. And of course, for us humans, time is even more ubiquitous in our lives. As Dean Bonamano mentions at the beginning of his book about the neuroscience and physics of time, the 3 out of 5 most frequently used English nouns are time, year, and day, with the other ones, I believe, being person and way, which in a way indicates the importance of this dimension in our everyday lives. The representation of time is, of course, almost equally important for any sort of agency, either biological or artificial. For example, an RL agent in many cases should be able to give answers to questions like, do I have enough time to execute an action, and when should I start? Or even, for how long should I remember something, and in some cases even whether time must be passing fast or slowly for a human being right now in order to be able to interface with us and have meaningful communication. Despite this importance, I believe that you would agree it is currently not very clear how the perception of time should be integrated in RL, and in fact, it's not even quite clear yet how exactly time is perceived by us humans and other animals. So this exact theme is the core of the workshop today. What do we know about how time is represented in the brain, mainly in an algorithmic level, and how does this knowledge from neuroscience helps us to understand where time has its place in artificial agents? Our speakers today will give us some extremely useful insights with regards to the field of reinforcement learning and the symbiosis with the field of neuroscience. Initially, we have Professor Richard Sutton from the University of Alberta and DeepMind, who will focus on the fundamental aspects of temporal representations in RL. And then Professor Mark Howard from Boston University will talk about temporal memory in the brain in RL. We had scheduled a third amazing keynote, but unfortunately our speaker was diagnosed with COVID, and due to the rules of the conference, we are not allowed to give online talks, so unfortunately we had to cancel that. Then, after our speakers, we will have a hackathon session that will last for about 2 hours, where initially we'll divide participants into moderated groups. All groups will be given a list of open problems in the field to discuss and propose solutions, and then groups will nominate a representative who will eventually participate in the panel discussion to present and defend the group's position to the rest of the workshop's participants. Although online active participation is not allowed, as I mentioned before, unfortunately, most of those parts will be streamed online, and we'll do our best to pass online audience questions during the event. Moving back to the introduction of the topic, the literature of time perception in neuroscience and psychology is really wide, although perhaps time still hasn't received the attention it deserves, but still it's quite wide. So me trying to summarize key findings or even theories would not do justice in the field at all. For example, here we see the Time Research Forum community, or TRF, which is a very active community running, amongst other things, conferences, particularly for research on time perception. Like the one here I have this picture from, which was held in Strasbourg, France a few years back. Although I expect the field to have grown even more since then, you can see already here that we're talking about relatively large conferences taking place regarding time perception. So, since I can definitely not cover everything here, we thought that it is a good idea to instead talk about a few key ideas or insights from the literature that have influenced our work in the topic. First, we know that when people report duration of events, they tend to regress these reports to the mean duration of all trials they have experienced. We know that their errors increase logarithmically with the actual duration magnitude, and they are more biased by the most recent trials. And we know also that All those aspects can be captured with Bayesian observer models that have been used in the literature for more than a decade now. We also know that when it comes to duration reports, the cognitive load of participants matters, as well as whether they need to use their memory to recall an event. Finally, we have multiple indications that physiological signals such as neural dynamics or cortical oscillations or even the heartbeat play some role in inferring time durations, although there has been, I have to say, some criticism regarding the extent to which this is true, and I'd like to point you to our paper cited here if you're interested to hear more about this topic. From our own research, we've been working for a few years now on the proposal that humans experience time as a measure of accumulated salience or surprising events in our hierarchy of perception, which in a way is like we're keeping track of how much energy our brain needed to processing an event, and we use that as our evidence about how long this event was. We've shown that this is the case while people are watching real-life videos, with evidence using deep neural network models of perception and with bold activity of fMRI from the corresponding cortical areas, while we showed that the same kind of activity from different cortical areas doesn't correlate well with behavior in the same way. What is interesting here is that starting from this basic idea of time perception as accumulated saliency, we can define what is a building block of subjective perception of time for both brains and artificial agents. First of all, when we're using a model of the environment, we can easily estimate surprise as some form of prediction error, such as the variational free energy of the agent in the level of latent representations. Thinking about surprise in terms of latent representations gives us a nice way to define events that are recorded and recalled in episodic memory, where boundaries of those events are simply changes in latent representations. And we've recently seen that when we calculate this kind of event boundaries using probabilistic models and we compare them to what actual humans report that perceive as events, these model boundaries match substantially to human subjective reports, which is quite interesting to observe and quite a nice validation of our initial assumptions. So connecting these insights, we have created a framework where we view episodic memory and time perception as two highly intertwined things. And we can show that counting new episodic events can account for prospective duration judgments, while counting recalled events accounts for retrospective judgments that require memory. So how about model-based agents? Currently, one major way in which agents differ in terms of their perception of time could be attributed to the assumptions they make about the world's dynamical structure. For example, you're all aware of simple discrete time Markov process. An agent based on a simple MTP would learn the world as a sequence of evenly spaced states evolving over time, and therefore it would rely on what we call the objective or physical timescale of the environment, where each state changes every time the environment ticks. However, if we take advantage of how we defined salient events in the previous slide, we can imagine different ways of modeling world dynamics using what we call subjective timescale of the environment, which basically means using only states that were selected by the agent itself in some way. Not necessarily via surprise, using some form of change point detection technique, but the important property is to be intrinsic to the agent. These subjective timescale models can be either flat or follow a hierarchical structure, and I would say that this is a topic with growing interest recently, at least in groups like ours. When it comes to flat subjective timescale models, there are multiple proposed papers over the last couple of years. They use different methods to select states, they use different representational capabilities, which ultimately, of course, affect the agent's perception of change or time, while hierarchical models are much more recent in general and mainly focus on a fixed temporal abstraction and represent multiple timescales in a nested way. A few months back, we attempted to combine those ideas in a paper which is in this year's ICLR, where we propose a predictive coding style generative model with nested timescales, where in each level of the hierarchy, states update only when the corresponding representations of the world in this level change. This is an unsupervised model which is able to capture the spatiotemporal structure of the world in a very promising way, in my opinion, which can be shown to be optimal in the sense of the structure of the network, and I would invite you all to have a look at our website if you're interested in the topic and check out the model. Finally, as you can guess, most questions in the field are still quite open. I would say that we need to understand what are the benefits of having explicit temporal representations versus having implicit temporal representations. That is, having an exact mechanism, for example a clock, as opposed to having an inferential mechanism, which is an approximation to physical time. We also need to understand the difference between modeling using objective versus subjective timescales. And we also need to decide whether we should consider the problem in a much deeper way, for example, via causal inference, and go back to physics and to the definition of the arrow of time. And finally, we need to understand the connection between the representations of time and space. I know that there are a few proposals out there that connect these concepts, for example, successor representation, but I have the feeling that we can do much more in this topic. So I'm sure that we can all come up with many more questions about time, but we feel that these ones provide a great start, and therefore they will provide the basis of our discussion in the next section of the workshop after our talks. And with that, I would like to thank you again very much for coming today, and let's quickly move to our amazing speakers.